Let's see how TensorFlow 2 and Keras make it easy to write those models to build pretty cool neural networks. tf.keras, again, that's TensorFlow's high-level API for building and training your deep learning models. It's also really useful for fast prototyping, state-of-the-art research, and productionalizing these models. And it has a couple key advantages that you should be familiar with. It's user-friendly. Keras has a simple, consistent interface optimized for your common ML use cases. It provides clear and actionable feedback for user errors, which makes it kind of fun to write ML with. Its modular and composable Keras models are made together by connecting configurable building blocks together with just a few restrictions. Also, it's really easy to extend and write your own custom building blocks to express new ideas on the leading edge of machine learning research. You can create new layers, create new metrics, loss functions, and develop your whole new state-of-the-art machine learning model should you wish. Here's an example. A sequential model, like you see here in code, is appropriate for a plain stack of layers, where each layer has exactly one input tensor and one output tensor. Sequential models are not really advisable if the model that you're building has multiple inputs or multiple outputs, any of the layers in the model have multiple inputs or multiple outputs, the model needs to do layer sharing, or the model has a nonlinear topology, such as a residual connection or if it multi-branches. Let's look at some more code. In this example, you'll see that there's one single dense layer being defined. That layer has 10 nodes, or neurons, and the activation is a softmax. Now, the activation being softmax tells us we're probably doing classification. With a single layer, the model is linear. This example is able to perform logistic regression and classify examples across 10 classes. With the addition of another dense layer, the model now becomes a neural network with one hidden layer. But it's possible to map nonlinearities through that ReLU activation we talked about before. Once more, you're going to add one layer, add to the network. Now it's becoming a deeper neural network. Each additional layer makes it deeper and deeper and deeper. Now, let's try that again. Here's another deeper neural network architecture. Needless to say, the deeper a neural net gets, generally the more powerful it becomes in learning patterns from your data. But one thing you really have to watch out for is this can cause the model to overfit, as it may almost learn all of the patterns in the data by memorizing it and not generalize to unseen data. Now, there are mechanisms to avoid that, like regularization, and we'll talk about those later. Once we define the model object, we compile it. During model compilation, a set of additional parameters are passed to the method. These parameters will determine the optimizer that should be used, the loss function, and the evaluation metrics. Other parameter options could be the loss weight, the sample weight mode, and the weighted metrics if you get really advanced into this. What is a loss function? Well, that's your guide to the terrain, telling the optimizer when it's moving in the right or wrong direction for reducing the loss. Optimizers tie together that loss function and the model parameters by actually doing the updating of the model in response to the output of the loss function. In plain terms, optimizers shape and mold your model into its most accurate possible form by playing around with those weights. An optimizer that's generally used in machine learning is SGD, or stochastic gradient descent. SGD is an algorithm that descends the slope, hence the name, to reach the lowest point on that loss surface. A useful way to think of this is think of that surface as a graphical representation of the data, and the lowest point in that graph as where that error is at a minimum. Optimizers aim to take the model there through successive training runs. In this example, the optimizer that we're using is called Atom. Atom is an optimization algorithm that can be used instead of the classical stochastic gradient descent procedure to update network weights iteratively based on the training data. The algorithm is straightforward to implement, and besides being computationally efficient and having little memory requirements, another advantage of Atom is its invariability due to the diagonal rescaling of the gradients. Atom is well suited for models that have large data sets, or if you have a lot of parameters that you're adjusting. The method is also very appropriate for problems with very noisy or sparse gradients and non-stationary objectives. In case you're wondering, besides Atom, some additional optimizers are momentum, which reduces learning rate when the gradient values are small, eta grad, which gives frequently occurring features low learning rates, eta delta improves eta grad by avoiding and reducing LR to 0, and the last one, which is a pretty cool name, FTRL, or follow the regularized leader. I love that name. It works well on wide models. At this time, Atom and FTRL make really good defaults for deep neural networks, as well as linear models that you're building. Now it's the moment that we've all been waiting for. It's time to train the model that we just defined. We'll train models in Keras by calling the fit method. You can pass parameters to fit that define the number of epochs. Again, an epoch is a complete pass on the entire training data set. Steps per epoch, which is the number of batch iterations before a training epoch is considered finished. Validation data, validation steps, batch size, which determines the number of samples in each mini batch. Its maximum is the number of all samples. And others, such as callbacks. Callbacks are utilities called at certain points during model training for activities such as logging and visualization using tools such as TensorBoard. Saving the training iterations to a variable allows for plotting of all your chosen evaluation metrics like mean absolute error, root mean squared error, accuracy, etc., versus the epochs, for example, like you see here. Here's a code snippet with all of the steps put together: the model definition, compilation, fitting, and evaluation. Once trained, the model can now be used for predictions or inferences. You'll need an input function that provides data for the prediction. So back to our example of the housing price model. We could predict the house prices of examples of a 1,500 square foot house and an 1,800 square foot apartment, for example. The predict function in the tf.keras API returns a numpy array or arrays of the predictions. The steps parameter determines the total number of steps before declaring the prediction round finished. Here, since we have just one example, we set steps equal to 1. Setting steps equal to none would also work here. Note, however, that if the input samples in the tf.data dataset or a dataset iterator and steps is set to none, predict will run until the input dataset is exhausted.